Welcome to another teardown and test video. This time it's another radiometer. It's a distortion meter type BKF5H. I had to take this out of its casing because I heard some loose items in there. So it was the mains connector that was cracked, and I just removed the parts, so that means we are ready to power it up and see what happens. This is an all-tube device. I can't find any manuals or anything online, but if you know your radiometer stuff, you will know this type of front panel design. That is what they used in the 1950 series of equipment. If it's from 1960 or newer, you'll see silk screens directly onto the paint. So this is 1950 design of a radiometer. So look at that oscillograph. Don't you just love that? I don't know the name of this connector, but it is like a shielded banana kind of type. You can access this with normal bananas, and then there's a convenient ground banana. They use a chassis as a ground, so it's fairly easy to access. The meter is really big and nice, easy to read. There's a little light bulb here, very nice and convenient, so you can read this if there's a dim light. There is a really nice gear ratio. Look at that. So that means you will be able to set the frequencies really nice and accurate. The different frequency ranges, that is a little bit funny. Okay, so this is from 200 to 20 to 200, right? So this is now 20. Okay, that is how it works. So that is fairly easy. Then it is the 200 to 2000, what it says, and then you can multiply it again. Okay, super cool. We can cover the entire audio area. You see, from 20 hertz to 20 kilohertz. Super nice. So this is very useful for audio amplifiers. We should be able to detect distortion. How about we just look at the rear, because now it is open anyway. So what I found inside the case was actually the mating part for this. It was broken and halfway inside the case. So I was afraid it was something important. So that is why I just don't power stuff up with loose items in there. I am a little bit worried about powering this up. See, the condition of this fuse is not so good. The voltage selector is really easy to figure out how to operate that one. I kind of like this design. Take some screws, and you can't accidentally screw this up, right? You need to think about something. You can't just flip-flop a switch and then break something, and you need to power it off before you change the voltages and such. So this is really a good way to do it, really. But I think I need to maintain this fuse before I power it up. This is not going to work, right? Don't you just love it when it is nice and shiny? I think this is a little bit bended. But anyway, now it looks like there's a much better and stable connection, and we should be able to get started. Okay, this is also okay. Those lovely old instruments need a little service before you just plug stuff in. See, the isolation here is just dangerous. I think I need to put on a new wire, huh? Maybe it's a little bit better up here. Doesn't feel so good. So what do you think? And I guess I think it is about time to change this, right? Did they have more fires, electrically fires in the old days? That was a bad decision to make cables like this. I think we are ready. I put everything here in the middle. And this is 1000 for 1%. This is off. This is off. Okay, and we power on mains. Huh? There's no. That is not good. Switch is not working. Kom nu, mand. Oi. So this pot meter is crazy. We need to operate this a little bit more. Ooh, I need to have an earth connection to this, because when I touch the casing, oi. Or maybe I just swap the mains connector. Yeah, okay, that helped. Now I can touch the plate. I swapped the mains connector. Okay, let's try and input something. There's clearly something working here. I don't know if I'm able to show you guys this. Let's see, this is the level. And then when I tune the... Okay, I need to input something, okay. Clunk. And then we dial down the level. There's not a lot of reaction around the center frequency now. I see a lot of loose. See? I am inputting 1 kilohertz, so that is why I wanted a response around 1K. What it is? Yeah, now it's working, right? See? Aha, see, there's a powerful dip at exactly 1 kilohertz. Let me see if I can show you guys this. This is 1 kilohertz. This is so shiny, it's impossible to show, really. See? And then, whoa. So, the filters and all that stuff is actually working. Yay. But, see? Ooh, it's... No matter what I touch, it just goes bananas. So all the pots, all the knobs, everything, all the switches is just full of loose connections. And that is actually its problem. So let's look inside. Inside the case, it's just so beautiful. They even numbered all the tubes. See? This is number 1. And this is the input. So the first tube you see on the input, this is the signal path. I guess 1 and then 2. And then you go over here. EF86, number 3, 4 and 5, 6. Fantastic. And then now is something funny. 7 is the EC80, so that is a diode tube. So this is the DC supplies. And number 8, I guess that is a voltage regulator and neon bulb, isn't it? I will see if that is right, because then it all makes sense about the numbering. Pretty good. I really like the way that everything is laid out here. Really, really nice. See the DC decoupling capacitor on the input? Isn't that just beautiful? Okay. The way that they mounted wires and stuff, or components as wires, is just beautiful. Look at that one. This will be for the filter section, I guess. And this capacitor is even mounted on top of some plastic, so that the casing here is not creating an unwanted capacity to chassis. So that is a pretty neat detail. This is the gearing for the frequency setting. So there's a spring coupling, and it also works as a hold, so it's not too loose. Yeah, this is a really genius design, because this is always going to work. And also this is a little bit flexible. So that was a good design. Series resistor for light. Lys is the Danish word for light. And the series resistor for that, so you can adjust the brightness. I bet the brown wires, that will be filament, 6.3 volts for everything. And the mains transformator is standing in a really weird way. Why is it standing up? So all this weight is up here, and the mains input and the fuse and selector is down here. Why isn't it the other way around? That is a little bit funny. Jensen capacitor, paper capacitor, so they will last forever. Maybe 63, but I think this design is 1950s. If I look at the front plate design and everything like that, so okay, man. So this is the bottom parts. Let's have a look. Okay, yeah. So that was the rectifier diode tube, remember? And then it goes to some more capacitors here, and the capacitors here. And what we got in here, that will be filter chokes, 2 of them. Oh, let's get some light. So that will be filter chokes for anode supplies. And that is the oscillograph output. Everything here is nicely shielded. I kind of like that. It is just beautifully made with the cables. Good thick. And what we got in here, that is a lot of capacitors, or adjustable capacitors. I would like to see what is in here. Whoa. They really mean business with those capacitors. And that will be super fine trimming of those values. Really? Oh, we also got some resistors up here as well. I don't know if that is easy to see. But all the way here, we got resistors and capacitors. And that will be the frequency ranges. Yep, it's exactly what I thought. A real nice variable capacitor with ball bearings and all. Yay! And look, it is isolated, standing on plastic and everything. So it is only connected. Oh, yeah, via those 3 wires. Ooh, that is sexy stuff. They really mean business with high impedances and all sorts of fancy. Oi, 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 oi. Also, when you see the height over ground of signals like this, you just know that, ooh, this is high impedance stuff. But then why is this so flat? So why is this not important? Right? This one should also have been like this, I guess. And remember that one? So that is exactly what I thought. A voltage regulator tube. And they are really, really beautiful. What you should try and do is rotate it where you can see, like this. Here we can see something inside, and then we take our little high voltage neon tester, and we can see it lights up. Yeah. Let's try and dim the light a little bit. Nice. Did you notice that all the tubes are EF86, right? More or less. And all the EF86 over here, they are not marked. But in the input section, see? This EF86, there's a red dot in the top. And this one is here. There's also an EF86 with a red dot. And that is, of course, this is the input section where noise is important. So the 2 input tubes, they got red dots. So you put the red marked dots tubes back into the input section because they are specially checked for lower noise. So when you service old tube equipment like this one and everything is a little bit loosey and funny and loose connections and stuff, just take all the tubes and move them around in circles, also a little bit up and a little bit down, around in circles for a little while. Don't be hard or anything, just slow and nice. So now there's a good fine connection in this tube again, and proceed through all the tubes. I've been cleaning the contacts a few times here, and I don't know, it's the 3rd time I take off this cover now. But now I realize it's actually a little bit difficult to hit exactly the right position. Look what they did. Those are the screws for the variable capacitor. Look at that. They actually hit. So it's a little bit difficult to get this into correct position. So you need to push this a little bit like this while you put in the screw. And this is of course what happens when you design stuff without 3D and without CAD, because this is done in 1950. So it's actually impressive. They didn't do any more errors, but that is definitely a design error. After a few hours of extra cleaning of all switches, this thing is actually working. So here's how it works. You put this dial into calibration mode and you adjust your input level. So if you see here, you put this for calibration. So this reads full. I connected my oscilloscope to the output here, just so we can see what is going on the output. So now we are in calibration. So now you flip to 100%. So there's nothing. It has something to do with the frequency adjustment here. So of course you aim for lowest signal. So that is the lowest in 100%. 50, 25, 10. Okay, so now we're in 10%. And again, we try and reach the lowest possible. Now we take the balance button and we adjust for lowest possible. Ooh, this is very critical. 5%, 2.5%, 1%. So 1% distortion is full. And we can, I don't think we can touch this one again. But then, ooh. So it's a matter of super carefully. Let's see if I can make this. So what you see here on the scope is actually all that noise added onto the signal here. So that is pretty cool. So 0.9, I think I had it to 0.7 when I was really good with this. And also it's drifting a little bit. And also super fine tuning here. Yes, look. It is really difficult. So that is 1% of full scale. So 0.5. So that means I should be able to flip this, right? So now it's 0.5. And look again. The balance button can go. All the way down. So 0.01 is the best I can make it. And see, it's drifting. And that has something to do with frequencies, of course, as well. But now we'll see almost only the noise that is coming out of my signal generator. I could also go in my signal generator now and go into fine stepping of the frequency. I don't dare to do that. But anyway, that is how it works, and I'm happy I was able to make it work and to measure 0.1. I think this is the best this meter can read. Ooh. So it really works. And soon it will go up for swap to somebody else. Hopefully they will be happy.